In this video, we're going to talk about section 9.3, where we're going to talk about two sample t-tests of means, and it's important to note that these samples come from independent samples. And let's look at some examples. So we're going to test the hypothesis made about two separate population means, and we're going to construct a confidence interval. Now, here are some examples of the independent samples that we need for this type of test. So we are looking at a reliability of a test assessment, and one group consists of 30 students and one group consists of 32 students. And I'm going to tell you when the numbers in your groups are different. That is the first clue that these are independent samples. So look for that first. Now, the other way that we do it is when our test subjects are not matched or paired in any way. So we have one group, and there should be an E on here, one group, and the second group, and so they don't say that they were paired in any way. That gives you the idea that they are independent. This is what we're going to do in this section. We're going to deal with data from two independent samples. We're going to assume they're in two separate populations, and we want to decide if there truly is a difference between them, and we might want to estimate what that difference is. So we're going to focus mostly on part 1. We are not going to do part 2. We'll talk about it briefly, but that's all that we're going to do with it. And the deal is that in part 1 we're going to use that sample standard deviation. So we are actually going to use S here. And that leads us to a t-test. Where in this one, when we know the standard deviations, then that would be a z-test of means, and that's a very artificial situation. So we are going to pay the most attention to part 1. So we don't know our population standard deviations, and we're going to assume that the standard deviations are not equal. So we need to make sure that we have independent samples. So they're either selected from one population or they're selected from two separate populations. But here is the most important piece. They are not related or paired. Now, in section 9.4, we are going to talk about dependent samples. And we talked a little bit about these the other night in class. So these are going to be before or after, or things that are matched on some criterion, husband and wife, brothers and sisters. So again, these are going to be in 9.4. Okay, so here is an example. We already looked at this. I think this is a repeat of a previous slide. And then this is an example of a dependent sample, that we have husbands and wives, and they are paired by couples. So again, this is going to be something we deal with in 9.4. Here is the summary of the notation that we're going to use. You can see this in your book in the tan section on page 486 and 487. You should be noticing that there's a pattern to our notation from one test to the next. Now again, here's what has to happen. We have to not know the population standard deviations, and we're not going to assume that they're equal. The samples need to be independent. They need to be simple random samples. And either the populations have normal distributions or we have large sample sizes. This is no different from when we had one sample tests of means. And here is the formula. Now again, I want to point this out. The mu values are the means that we are assuming in the null hypotheses. And remember, the null hypothesis says they're going to be equal. So this value is usually 0. And this is our sample standard deviation 1. We square it, divide it by n. Our sample standard deviation 2 squared divided by n2. We add those together and take the square root of that. Again, you can plug these in, you can hammer out the math, but you can put these values into StatCrunch and it will do the math for you. Now, degrees of freedom when we're doing a 2-sample t-test of means. On page 486 in your book, in the blue box, they have the formula for exact degrees of freedom. When we do this by hand, we are going to use the conservative estimate, and we're going to find n1 minus 1 or n2 minus 1. We're going to take the smallest value. Or when we use StatCrunch, we will have exact degrees of freedom. Then you can either use table A3 to get the p-value range, or we can use StatCrunch. And again, when you do this by hand, you're going to use the smaller of n minus 1 or n minus 2. This is a conservative estimate, and it means you will never reject the null hypothesis when you shouldn't. When you do it by hand, we're going to use table A3 to find the range of p-values. If you're going to use the critical value method, you would use A3 to do that. But what I want you to do is I want you to use StatCrunch. It's very, very important that you use StatCrunch to do this. Then StatCrunch will automatically give you the exact degrees of freedom and will automatically give you the exact p-value. Here is the formula for our confidence interval, and the first parts of these math statements should look familiar. Now remember, this is what we are estimating. So our middle statement with the mu's stays that way. This is going to be a number that we calculate, and it will be the same in the less than statement as in the more than statement. And then we use our critical value to find our margin of error. And again, if you're going to do this by hand, use the smaller of n minus 1 or n minus 2. You can find the exact critical value. You can find the error on StatCrunch, and we'll do some examples of that in just a moment. When you do this, you need to decide if this is a good sample, and you do want to verify the requirements, and that means that you have independent samples. One sample doesn't affect the other. It means that you either the population is normally distributed or you have samples of size more than 30, and that it's a simple random sample. Okay, so this is the example that's in your book at the beginning of the chapter, and so that's on page 471. And so they put people, and I would have said this different, they put people in a red room, and they asked them to think of creative uses for a brick. And then other subjects were put in a blue room and asked to do the same thing. And then a panel of judges did the data gathering. So the researchers make the claim that blue enhances performance on a creative task. Test the claim using a .01 significance level. So right there, those keywords, test the claim, you should be thinking, aha, 6-step test. We don't know the population standard deviation. We can't assume they're equal. The groups are independent because they were gathered separately. The samples are simple random sample, and both samples exceeded 30. The red group was 35 and the blue group was 36. So all the requirements are satisfied, so we can go on. And here is the data, and this is the same data that we find for the creativity on page 471. This is the table that you're going to put in step 3. So here we go. Step 1, we want to decide what our hypotheses are. And so again, if the blue background is group 2, and I would recommend that you put this as a note in step 1. And if group 2 is more creative than group 1, then our sign in our alternative hypothesis should be that mu1 is less than mu2. And so here are our hypotheses for step 1. And I did not do this correctly because back in the original problem it said, where did I find it? 0.01 significance level. So let's go back and let's get rid of this, and it should be 0.01. And because we don't know standard deviations, we're going to use a t-distribution. So step 3, we would slip in that table that you can see on page 471, or that was on a couple slides ago. And here we go. We plug in our numbers, and we come up with a t-score. Now we need to find a p-value. So we could either find the critical value. This is the critical value method. And our critical value was, you'd look up on the table and you'd find 2.441. But because we have a less than statement in our alternative hypothesis, we know that's going to be in the lower tail. So then you would say your critical value is a negative. And is our test statistic further out in the tail than our critical value? Yes, it is. Now, because we use the table, we're going to use a conservative value for our degrees of freedom. So our degrees of freedom would either be 34 or 35. We use the smaller one. We use 34. So now what does this mean? Our test statistic is farther out in the tail. So that means in step 5 we can reject the null hypothesis. And I would not put that statement with the mu's on there. Now, technology is going to give us the p-value is 0.0021. That's less than our alpha level. So again, we're going to reject the null hypothesis. So remember that using the critical value method or the p-value method, you will always get the same answers. And so there is sufficient evidence to support the claim that the red background group has a lower mean creativity score than the blue background group. So I basically would have said this the other way. This study suggests that the blue background group had a higher mean creativity score than the red background group. Now let's go ahead and let's construct a 98% confidence interval. We use alpha equals 0.01. It was a one-tailed test. Now when we go to a confidence interval, that becomes a two-tailed test. So basically what we did here was we doubled alpha and subtracted from 1 to get this 98% confidence level. And we're going to go ahead and do our critical T. We're going to calculate the rest of our margin of error, and here is where we get our margin of error. About a half a point of creativity. And so what we're going to do is we're going to subtract x1 minus x2, and that's where we get the number that we subtract our confidence interval from. So our confidence interval ranges from a negative 1.06 to a negative 0.10. Notice that 0 is not in that interval, so we would estimate that the difference is less than 0. And that's what this slide says. Okay, let's take a break here and let's do StatCrunch so you can see how to do these two tests with StatCrunch. Okay, let's look at how we're going to do that same problem regarding creativity using StatCrunch. So I'm going to go to Stat. I want to do T statistics. I'm going to do to sample with summary. And my sample mean 1. And remember, 1 was red and 2 was blue. So sample mean 1 was 3.39. And the sample standard deviation was 0.97. And my sample size was 35. And then my sample mean 2 was 3.97. The standard deviation was 0.63, and my sample size was 36. We don't want to pool our variances. What that means is we are assuming that they're equal, so make sure that that box is unchecked. Let's go ahead and let me move this over here. So it's in the middle, and I'm going to do my hypothesis test. And now I have to think about this a little bit. It was mu1 is less than mu2, so that means the difference would be less than. And again, our null hypothesis is that they're equal, so their difference would be 0. And go ahead and compute. And you can see we get the same t statistic and we get the same p-value. What I do want to point out is that our degrees of freedom are quite different, and that's because StatCrunch uses that big honkin' formula that was in your textbook for degrees of freedom. So this is going to be exact degrees of freedom. Make sure you uncheck that box. And then again, we're going to do a 98% confidence interval. And here we go. Notice our degrees of freedom now are the same. And here is our lower limit and our upper limit, and that should match with what we found. Well, it'll be close by what we found using the table, because remember, our degrees of freedom were different because we used the conservative estimate. But make sure that you unclick the box because you don't want to pool the variances because we are not going to assume that they are equal. And then to finish up this section, we are going to follow the recommendations by people who know better than we do, and we are going to assume that sigma is unknown and do not assume they are equal. So in other words, we're just going to use part 1, and that's why it's important on StatCrunch to uncheck that pooled button. Here is a flow chart, and basically where we are going to go is we are going to look at this, and we're going to start, and we don't know our population standard deviations. We're not going to assume that they're normal, so right here, this is where we're going to go. And so we are not going to use this method for our standard error, and we are not going to use this method. So we've looked at independent samples where we do not know the standard deviations and we assume they're not equal. We decided we're not going to do the method where the standard deviations are known, and we are not using the alternative method where we assume that they're equal, and so we pool them. So this is how you do testing means from independent populations. In the next section, we're going to look at dependent sampling, which is referred to as matched pairs.